Okay guys, I think we'll begin. It's not too many materials that I have. We should be over in about 30 odd minutes, and then if you have questions, just keep them asking in between. That's not a problem. We'll just keep this interactive as we go along. So any questions you have, just ask. So this is basically about what's new in SCMI. There are certain new power models that can be now enabled via SCMI. So we'll clarify some of them, and then we'll talk about the features, new features in SCMIv2 that we have introduced and how to use them, and then hopefully some new features that we are planning for the next release onwards and the status. So this is what the SCMIv2 now looks like. If you look at the diagram on the side, you'll see that we have added a few protocols that were not there earlier. Basically, you see something called resource isolation that's added as a part of your base protocol. You've got resets that have been added, and the entire diagram, as you see, has been cleaned up a little. So you see that now you have got examples of agents over here. So you could typically have, this diagram shows you 3 agents. So you should have 3 agents, like a secure world firmware can be an agent. Operating system on a non-secure side can be an agent. You could have a third agent running somewhere else. And if you have a power microcontroller that runs your power coprocessor, then all of these agents can talk via SCMI channels to that platform controller, which is your SCP. And we have introduced a few new transports. So one is FastChannels for DVFS. That's on the bottom right corner. And then you can add your own as well. So there are people who are thinking of adding a few other stuff specifically for automotive. So these are the new features that we have added. I'll go into some of the details in the next slides. So now these are the new power management modules, models that can be enabled via SCMI. And this is again a very high level abstraction. Nothing. It just shows you what you can enable. So if you look at the diagram on the left, it shows you a standard normal world OS that talks to a hardware mailbox driver or any other transport. You could build your own transport for your own SOC. That's not a problem. And that talks to the power controller. And on the secure side, you could have an EL3 firmware that also uses the same channel to talk to a power controller. So this is your standard mechanism that we follow even today. The system and power control microprocessor over here, if you see on the right, that has now 2 implications in which you could run. So you could run the actual firmware on the microcontroller itself, or if you have a Cortex M3X series, you could typically have your firmware that runs on the secure side as well. So you see a small box called TFM and the small box called SCP. Let's not assume that they are in different worlds or one on top of the other. It just shows that they coexist on that side. But how it has to be split, how it has to be deployed is something that we are actually thinking, and it will become clearer in times to come once we have actual platforms that come up with these considerations. But just keep in mind that actual implementations like this is possible using SCMI, and the mechanism and the interface allows for all of this to happen. And the good part about this is that the OS doesn't know what's happening at the back end. So as far as it's concerned, it can be any of these models.
Sorry, the SCP boxes. The SCP box is just a driver, right? The orange box.
So that's your firmware.
Okay.
That's the same as an SCMI server.
Okay.
But here it works on a microcontroller's secure side.
I see.
On an M3X.
Okay, sorry, I misinterpreted the diagram, like seeing them as separate things,
Yes.
talking to that bit over there.
So basically, if you have an M3X and you want to do your own special stuff on the non-secure side, then you could have the power controller sit on the other side. And that's all it means. It doesn't. There are no different worlds over here. We are not implying anything else on this apart from the fact that it's on the secure side.
And in the case where you have the trust and isolation boundary, the CPO/the SCMI server, that would be a part of the platform root of trust.
That depends upon what the architecture eventually emerges to on platforms like this. I don't have any more information of that at this point in time. It's
Fair
just
enough.
a possibility, and it has to be investigated further. So now these are again two different deployment models. On the left, you see an SCMI driver talking over SPCI to a secure world SCP implementation. That's what we have been trying to implement using the session that we saw last. And you see on the right-hand side, you'll see that the SCP firmware is there in platforms which just have a very simple EL3 sort of firmware running with nothing on top, no trusted OS, nothing else. So it's basically a very simplistic implementation of it. If you don't want to implement anything at all in your secure world, and if you just have an EL3 firmware, you can put the SCP as a platform library somewhere over there.
Just to be clear, that picture on the right is against the direction of travel for trusted firmware, so probably wouldn't be upstreamable.
Yes, it won't be upstreamable. So you can maintain that in your own repository, yeah, of course, but we cannot merge it in because everybody will have their own platform libraries and we can't maintain all of them together. Yes. Okay.
Just
So-
one question, sorry. Could you clarify one thing that for the power management, it's just for the CPU idle or also for the, for example, the CPU frequency or for the...
Okay, yeah. So I'll come back to the slide. So if you see here, there are actually two types of protocols that exist. One is SCMI. The other thing is PSCI. So PSCI is the gray box that you see on the right-hand side. So the gray box is connected to system and AP power. That means your CPU-specific idling things, so CPU idle, CPU suspend, and a CPU reset, go via PSCI. And then PSCI can talk SCMI to the platform controller, right? For everything else, device idling, device power, your power to gen PDs, clocks, resets, everything else, you can use SCMI. So that's the overall split that we have right now. So if you look at the kernel that we have, there is a Juno upstream implementation that we have in the upstream kernel right now. So that has a very nice split of how the thing is supposed to work.
So for the CPU frequency this side, that the kernel can directly to send out to the SCMI the request to the, for example, don't to through the secure world, just to from the non-secure world to send out the request to the MCU.
Yes, you can directly send it out.
Oh, okay.
Yes, and that's a part of your performance protocol. So not only that, the performance protocol handles not only your CPU frequency, but potentially a GPU frequency. If you have an NPU that's clockable, different NPU frequencies. If you have DDR that is clockable at different clock rates, then potentially DDR frequency considerations as well.
And I guess that depends on the presence of a non-secure channel as well with the controller.
Of course.
So if you just have single channel, then you have to go by the secure world.
Yes. Okay, so resume from here. So this is typically for automotive systems. So in automotive systems, you might have multiple VMs that are running and a hypervisor. Take your pick, whatever it is. And here you see that the SCMI driver over here talks to a mailbox driver, and that over a virtual channel talks to the virtual SCP that sits on a hypervisor. So there are hypervisors which will implement a virtual SCP, which can be a complete implementation of an SCP or a partial implementation of an SCP. But what it does is it exposes a virtual channel to each of your guests, and your guests can send SCMI commands over the SCMI channel to the hypervisor. And then the hypervisor, depending upon what the platform configuration is, in this example, there is no separate microcontroller. So what the hypervisor does is that it further uses an SPCI to communicate with the secure world where your SCMI server or SCMI service is actually running. So the benefits of this is that each of your virtual machines over here are standard Linux bodies. You don't have to modify any of them. They run out of the box. So each of these VMs don't know what's extra or what's there or what's not there. They just use the SCMI channel that's available to them and that they discover at runtime, and then they use it as it is. So on your standard automotive systems, this is a mechanism that's now enabled.
So do we have anything in the spec where there's a coordination between these notifications which reach to M cores?
Okay, yeah, I'll talk about that as well.
Okay.
Yes. Okay, good question. So here, there are two models, and I've actually combined them into one. So you could typically have nothing here, and you could have the entire power control logic here. But that's a very dangerous thing to do. That means you're trusting your hypervisor implicitly to maintain the sanctity of your entire system. And then if it sets things on a wrong path, you literally have no control of your device anymore. So the recommended path is have a small wrapper implementation here, which is a small SCMI server that just takes the SCMI command, interprets it, further sends it across to the secure side where your actual logic is, if you don't have a microcontroller. But most automotive platforms, at least going on to the future, will have a microcontroller because you're going to run a lot of VMs and a lot of different modules on it, your head units and cluster units and so on and so forth. So you will have the budget as well as the power budget for a microcontroller as well, and the BOM area as well.
But do you expect like a reason for the hypervisor to host anything there, or the CPU VMs are free to just go direct to the?
No, the hypervisor. So in this model, as you can see, the hypervisor gives particular mailboxes. So the hypervisor reserves, let's say 96 bytes for each channel, and each of these channels are then exposed to each of the VMs. So whenever the VM writes to that channel, you basically trap into the hypervisor. So it's a virtual channel. The VMs don't know that it's a virtual channel. For them, it's the same as a physical channel. But when you write into it, it'll basically generate a trap into your hypervisor because you're writing to a virtual space.
Right. So if instead of the mailbox, if they were using SPCI, they'll just go.
Yes.
Yeah.
So here you can just write, and it goes over here, and it goes through.
So is it possible for the VMs to use SMC/SPCI to talk to the hypervisor while using SCMI as a protocol? What I'm trying to get at is that in the earlier diagrams, if there was no hypervisor, then the SCMI driver is essentially relying on some SMC-based transport to talk to the secure world. And this seems a little different from that because the interface between the hypervisor and the VM is now different from the earlier diagram.
Yes. So, okay. So what we have done over here is a virtual channel. So what this means is this is not an SMC driver over here. You could have a potential an SPCI-based mailbox as well, which will again use the same SPCI mechanism to go through.
So that's not off the table.
That's not off the table. Okay. So here, if you notice that the hypervisor can still use SPCI if it wants.
Yeah.
Right? You could potentially have an SPCI here as well. But if this thing says, I don't support SPCI, I only support a standard hardware mailbox, then you use a virtual channel using a standard hardware mailbox, which is basically a pseudo mailbox or a virtual channel that the hypervisor exposes, and then you go all the way through.
Yeah, one of the other reasons I'm asking that is because if the hypervisor wants to take no responsibility for any SCMI traffic, then if SPCI or say the SMC mailbox is being used inside the VM, then the hypervisor can just choose to forward those SMCs possibly blindly into the secure world and have none of it. Basically, like I don't want to even interpret whether this is SCMI traffic or not. As far as I'm concerned, it's just an SPCI call which I'll transfer into the secure world. So that kind of an implementation, do you think that would be possible?
There are a few considerations there because SPCI, if you want to expose that through SPCI, then you have to have the capability to have multiple SPCI channels exposed from the secure world to each of the VMs. And then a mechanism for each of the VM to discover their own SPCI channels.
Right.
To the secure side. So once you have that plumbing in place, you could do it.
Okay.
Yes.
Okay.
But again, I'm saying for an automotive platform, most implementations going forward will have a separate microcontroller. This is just a worst case of effort for platforms right now which don't have a microcontroller and which are stuck. It's not a recommended approach because the load is, with multiple VMs talking power management, the load is going to be far too large to keep doing this. You're just going to lose a lot of performance.
Okay.
So on the other side, if you look on the right-hand side, you'll notice that the diagram on the non-secure side of the trust zone isolation boundary is still the same. So the VMs can talk directly to the system power microcontroller, to the virtual channels. On the secure side, you could typically have PSCI do the same. So this is an implementation where you actually have a power microcontroller, and each of them can then talk to a power microcontroller through a standard logic, and that is the recommended approach over here, and not on the other side. This is for platforms. If you don't have it, then you can use it. Otherwise, use it that way. It's far better. Okay, and so this is the other part that SCMIv2 potentially unleashes, and this is each of the VMs have their own direct channels to the power microcontroller. There are a few pitfalls, drawbacks here, is that obviously you have to create those specific physical channels, which means more memory considerations, a little bit more hardware. But the advantage is that your hypervisor is now completely agnostic of all what your VM does. So the VM can directly access the power controller, and the VM can send its power requests directly to a power controller. The hypervisor can do the same, and the secure side can do the same. Now, this opens up a few issues that you need to control what a VM asks to a power controller to do. And that is what the SCMIv2 enables you. It enables each of these channels to have a setting of their own. That is, you can forbid certain things on certain channels and isolate each of these channels. So that provides you a domain isolation capability through SCMIv2. And we'll go further into that in the next slides. So what I'll do is that, because I said that, we'll look at this slide first and then go back to the other slide. So this is what SCMIv2 does. So assume you have an automotive platform. If you look at the picture on the right, you'll see that you have, let's say, 7 resources, and you've got 4 channels, and let's say 3 VMs, 1 hypervisor. And so each of these channels can have their own resource isolation domains. That is, VM3 has access to only R7, VM2 has access to R5 and R6. And SCMIv2 allows the hypervisor or a single control channel owner, whoever owns that control channel. You could even have the secure side own that control channel, an entity on the secure side. That entity can actually configure what resources are accessible over which channel. So once that configuration is done, the channels cannot access any other resources over them. So if you try to access some other resource or try to say, I want a clock changed for R4, the power controller is going to return a denied to you because you don't have access to it. And obviously, the entity which controls the channel can tear down the channel at any point in time and reset it as well, and that's what SCMIv2 does. So the hypervisor or a secure entity will have access to all the channels, and each channel will have a unique agent ID, and that's allocated to it by the system controller. So when the system boots, the system controller knows that I've actually got 5 channels, and it allocates IDs to each of it. The IDs are discoverable, so when the system boots, the kernel can actually probe a channel and say, what's the ID? And it says, I've got 5 channels, IDs 1 to 5, and you know that these are the IDs of the channels. They're discoverable. And then the hypervisor chooses which channels to allocate to which VM. So it can say, okay, channel ID 1 goes to VM 1, or something like that. And then it can actually configure the access permissions of agents. So you've got 3 commands over here: a set device permission, a set protocol permission, and a reset agent configuration. So set device permission allows you to actually specify which devices are accessible over which channel. Protocol permissions gives you the capability to say, on this particular channel, for this particular device, only allow X protocol. That means if you have, let's say, a USB device, or let's say a GPU, if you have a GPU that you want to share with the entertainment unit or the IVI unit, you can actually say that the IVI VM has access to the GPU, but it does not have any access to the GPU's power domains. It just can control the GPU's frequency. So you can say only allow access to the performance protocol for the GPU for this particular VM, disable access to everything else. So then you can just control the power frequencies. You cannot touch the power domains at all. So that allows you a level of abstraction, a level of deniability, so that the VM cannot change anything else it wants. This is assuming that the host map of the memory map of the GPU is not exposed directly to each of the VMs. I mean, nobody is going to be foolish enough to do that, but let me just put in the disclaimer that your memory maps should be strictly limited, and you can't expose your entire memory map to everybody else. Reset agent configuration, what that does is that it allows you to tear down the particular channel and say, for this particular channel, I'm going to tear down this channel. Don't allow any access on top of it. You could do that. And you could really move an agent around, and you could say, this agent goes away, I bring in another VM, and you could basically then have a channel being moved on from one VM to the next, being allocated from one VM to the next with different configurations on the channel itself.
So the enforcement of access control will be happening at the SCP end, right? The hypervisor is merely expressing what kind of access control it wants. So even if, can this be done in the secure world as well? Because like if you have two channels and one's picked up by EL3 firmware and the other one's picked up by the trusted OS, it should be possible to kind of achieve the same end, right? Because the access control enforcement is at the slave side rather than at the master side in a way.
Yes. So in SCMI terms, the master is the SCP, the slave are the agents.
Okay, just turn it around.
Turn around, yes. So
right. And also, like if the SCP is implemented in the secure world and the hypervisor is trying to do the same access control, it should be possible to do that too.
yes, it should be possible to do that. And the SCP firmware is deployable everywhere.
Exactly.
You deploy it wherever you want, you'll get the same results,
okay,
provided you set up the plumbing correctly.
All right.
So what that means is that once the hypervisor or whoever it is controls all of this and sets all of this up, you can start up your VM with that particular channel, and you're good to go. And that works as usual. So how does it work? So on a particular device, you will have power domains, you will have performance domains, clocks, resets, GPIO, sensors, and all your different devices, right? I'm not put sensors in that because sensor is a device in its own right. So you can actually have a sensor as a different device. But for most other devices, let's say a GPU, you'll have a power domain that it resides in, a performance domain that it might have, 3 different clock frequencies, a few clocks that that supplies it, a reset domain that you can use to reset the GPU, and so on. So all of them can be abstracted into a device in your platform controller. So if you have a platform controller firmware, all of them, you club them into a particular device, assign that a particular device ID, right? And then that particular device ID, which is a 32-bit identifier, is something that the hypervisor can play around with. And the hypervisor uses those device ID to configure the channels. It seems a little counterintuitive at first because we do not have the discovery of these IDs built into the protocol right now. And there's a particular reason why we did that. The reason is that today, for ARM systems, device-specific handling of power management is not there in the kernel at all. That is something that we are trying to fix. That is something that we'll probably bring on with the next version of the SCMI. But for now, what we are doing is that we are setting up the basics. So if your firmware is capable of doing this, your firmware is already ready for SCMIv2.0. So you don't have to migrate your firmware anymore when a device capability gets built in. You have the basic abstractions. So what that means is that you do that and assign those devices to particular VMs. And the moment you assign a device to a VM, the VM has access to whatever is a part of the device. And of course, if you say that I don't want it to access the performance domain, you can say don't allow access to the performance protocol, and then the performance domain goes away. It just have access to the other 4 items over there. So devices can be logical. That is, you can pick and select any combination of things to mean a device. You dream up your own device and make a device of your own. Nothing stops you from doing that. It's highly flexible. Something like a debug domain can be a device. Although it spans a lot of things, it can be a little fuzzy. A debug domain can be made up into a device in this instance. Base set protocol permissions is what we use to remove access to a performance domain or any other domain if you don't want a device to access everything on the Otherwise, whatever comes to the device gets accessed automatically, and the VM can send commands to access all the resources allowed by hypervisor over a channel. So what it does is it takes care that you're not blocked by the kernel deficiency right now. The kernel functions as it is. The kernel still sees power domains, performance domains, clocks, resets, GPIOs, etc. The kernel does its work. The power controller does its work, and you're still able to set up resource isolation domains today. Somebody asks about A plus M class SoCs, or let's say, forget A plus M, you can have any class of SoCs, any combination of clusters thrown in together. So basically what that means is you have two masters, one being an A class which runs its own OS, one being the M class which runs its own OS. There might be a hypervisor at the bottom, there might not be. So I've chosen an example where bare metal OSs are running on the platform, two separate instances of bare metal OSs, and there's a single SCP that's there. So using the commands that I showed, you could actually even set up the entire system so that the M class can have its own specific set of resources, the A class can have its own specific set of resources, and the entire SoC can be partitioned out. So you have one SoC that has multiple clusters. Each set of clusters has access to its own devices or its own resources, and then depending upon the configuration of your SoC or what you want to deploy it for, you can fuse out certain devices, you can change the assignment of devices, all of this dynamically at boot up time through a device tree. So that's the capability that you bring it through here, and it's all done via SCMIv2 through those particular set of commands that I showed. So the commands do not need a hypervisor to work, it just needs a trusted agent to work. So in this particular instance, since none of them are trusted, it's probably an entity on the secure side that's going to do it. Or in your boot up process, whoever is your root of trust, the root of trust can partition the system in this fashion by using SCMI. Did that answer some of the questions?
Components on the SoC. So I'm not able to understand how a DDR type of resource can be partitioned, or if one VM has got a liberty to change the DDR configuration, because that is affecting the whole system. So do you have those kind of limitations addressed in your frameworks?
Okay. So I don't think I have a slide on that, but the way we do it, the way the philosophy on this works is each of these channels for each of these VMs. Okay, I have to go back, and there's a particularly interesting case over here. Here, if you see R4, that seems like a resource that's shared between master 1 and master 2. So that's something like a DDR, which has a clock shared between 1 and 2. And so what you do over here is that the SCP receives requests from both of them. One says change it to 400, one says increase it to 800, and then the SCP has a policy manager that can decide, okay, what do I do in this scenario? So it's up to your implementation. Both of your requests will come to you, and the standard SCP code that we have upstreamed right now, the requests come with its own tagged agent ID. So the SCP receives the agent with its own with its agent ID, and that goes to a particular module. So if you have a DDR module in your SCP, the DDR module will receive 2 requests with 2 agent IDs, and then your particular DDR module, which you have implemented, can then decide what you want to do with it.
So is there would be some kind of a policy there, like which request has to be entertained, right?
Yes.
This is
Which
what
request, or you want to just increase
ignore
the highest one or the lowest one, or if there is a thermal interaction and there's a thermal runaway, you want to do neither and drop it down to 200 instead. You could all do it in your own module, which you can plug it to the SCP firmware.
And there would be notifications to others, because this thing is impacting everyone, right?
Yes. So
that kind of thing is also.
Yes. The thing with notifications is SCMI supports notifications as a standard. The specification supports notifications where agents can actually ask for specific notifications that it's interested in. Currently, the the notifications are halfway there in the firmware that we have implemented. On the kernel side, as I did express earlier, that we didn't implement it for a long time because we didn't find anybody that was interested, but now we do have requests from a lot of people for notifications. So we are in the process of implementing notifications even in the kernel. It's just a matter of finding out a clean way of doing it and then having it, everybody accept it. Internally, we have prototypes where notification works, but we need to clean that up and upstream it.
Okay, thank you.
Maybe a follow-up question is that how about the QoS constraint? Yeah.
Okay. It's very nice that you brought this up because I was myself in two minds whether we should support QoS or not. Let me park that and take that for the next few slides, okay? Okay, this is SCMI fast channels. This is something that we introduced as a part of SCMIv2. So what this does is if you have an interface which is sort of a register based, like Intel has these Intel has these different registers into which you can write frequencies, right? In ARM, a platform might have a register, another platform might not have a register, but you could actually have every platform have a region of memory space in which you can just write your frequency requests. So SCMI fast channels allow you to do that. So today, an agent has got a channel, and all requests go in through that particular channel. But fast channel is a dedicated channel for a particular purpose. So if you say, I need a very fast DVFS, you could create your own channel just for DVFS without having to go through the entire SCMI header format. So a fast channel is very simple. It just takes in the request. There's no header, there's no other requirement. So if you want to change, let's say, a frequency, you can just write 600,000 into a particular region of memory, and that's it. That's all it does. On the other side, you need a way of knowing that somebody has written to that piece of memory. So today we have an implementation on a Juno platform because we don't have so many interrupts. We have a yielding loop that goes round and round every 4 milliseconds, checking if there are new interrupts. You can have it every 1 millisecond to check if there is any new writes to the fast channel over there. And so the moment you use a SCMI CPU flex set target to write onto your fast channel, the other side takes that. So what we have established over here is that this is really fast. Takes about a millisecond for the kernel to respond. So not a millisecond, sorry, about a few microseconds. The earlier response time was in tens of microseconds. We have been able to reduce that to 2 or 3 microseconds on the kernel side. So once the kernel writes it, it says, I'm done within 2 microseconds at all. So you could use it in a fast path if you would. So that's the benefit. The flip side is that you don't know whether your request is accepted or not. So if you're writing under thermal overhead, so if your system is thermally very constrained and it's overloaded already, it's already at 70 degrees, and you want it to go to 3 gigahertz, it'll not go to 3 gigahertz, and you'll not know that it's not gone to 3 gigahertz. And that's the disadvantage with every small channel constrained systems, right? Even with a register-based interface, you'll not know what your frequency is till you want to read some other register, right? So that's what fast channel is. It's just for writing one, and it's very fast. You don't need to implement anything else. There are no headers, there are no footers. We have got a implementation of this in the kernel, a few patches for it in the kernel right now. It should be merged pretty soon. So that's what I just wanted to briefly touch upon this. Okay, so now, because I think QoS, okay. Let me just bring this up first. Okay. Some other features. So reset domain management and SMC-based doorbell. So reset domain management is if you want to reset a particular cluster of devices or a peripheral, that's what the reset domain management does. It ties in very nicely to the Linux reset framework. It just gels in pretty well. So if you are using the Linux reset framework, it should be able to use SCMI implicitly. You don't have to do any more changes. It should just go through and through. You just need to select SCMI as the backend on the other side, and you're okay. You're all done. It just works out of the box. SMC HVC-based doorbells. So this is a concept that we did introduce for having future support for SPCI and other stuff. So all you need over here is that what it does is that it provides you a mechanism of communicating using SMC as a doorbell. Earlier, we didn't specify it, so people were going all over the way, doing everything that they wanted. What we have done over here is that we have tried to constrain it a little bit, so that now you have actually a way of doing it. So what we say is that you need a function ID and you need a 32-bit mailbox identifier to go on the other side. And the other side talks over this particular mailbox. So what that happens is that this will map to your SMC mailbox today, but in the future, this will implicitly map to SPCI as and when you move to ARM 8.4 and other platforms. Okay, so this is the device view. So if you look at the picture over here, the device and the abstraction of the device is something that I've already shown you earlier. That SCMIv2 already talks about as far as resource isolation is concerned. The right-hand side in green is the one that's missing in the kernel today. Now, we had a lot of discussions with a lot of kernel people, and it seems that the idea on the green part is eminently something that's missing, that we should be able to do. So today what happens is that if you want an SCMI request, or if you want to rather, if you rather would want to manage your power manager, if you want to manage power, the kernel has power domains, performance domains, clocks, resets, and so on and so forth. You have a huge DT that you need to build to make for your platform, and you need to do a power management through that. What this enables is that you actually don't need to do all of that. Your kernel knows what are the devices it has. So when the kernel boots in your DT, you already have a list of devices. So what SCMIv3 or the next version of SCMI will do is that it will give you a capability to control power implicitly on these devices itself, instead of the kernel having to enumerate everything of a device. So what happens over here is that your kernel can now remain unchanged whenever you move across from SOC to SOC. So for different SOCs, you don't have to modify your DT anymore. You don't have to tell the kernel that I've got 20 clocks, or these are the 20 different clocks. The kernel boots up with a list of devices, and it just says, set power state, set performance level, reset. That's it. And then the firmware already has got that mapping. The firmware does the rest for you. The left-hand side is something that we'll do internally. The right-hand side is something that needs to be upstreamed on the kernel. It's on our plans, and we'll do it at a particular point in time, but I wanted to show this to show that this is the simplifications that we are about to do. And once this gets done, then typically the same kernel will work on whatever platform you want to work on. You don't have to change your DT anymore. You just expose your devices, and that's it. You don't need to be aware of your platform power capabilities or your platform GPIO settings or your clock settings and your PLL settings and so on and so forth. It will save you a lot of time, and you can just have a native vanilla kernel working on different types of SOCs. Coming to this, once we have this, there was another idea that we have, was to have autonomous power management and QoS. Autonomous power management and QoS would apply to devices, but today we do not have sufficient requirements from people to say that I have a device that can be autonomously power managed, or I have a device that has autonomous power management via QoS. That is, on that particular device, you just set a QoS, you do not even do power management. The firmware or the hardware has the capability to autonomously put the device into different idle states or different power states depending upon the QoS that you have set. So now coming to your question, could you please elaborate a little bit further? What kind of QoS support were you exactly looking for?
So can I understand that the QoS actually is finished in the kernel side and not finished in the SCMI, is right?
So today the QoS that exists on the kernel side is largely symbolic, because you can just set a QoS, but what it actually translates into a hardware is something that's different from one hardware to the next, right? What it actually means is something that we have not yet understood. So I think before we can introduce the concept of QoS as a standardized interface, we need to figure out what kind of QoS do you actually want, what kind of use cases you are looking at, and what do you actually mean when you say a QoS. I mean, that definition by itself is very nebulous at this point in time. And that's why I asked you the specific question that do you have a particular use case in mind when you say QoS?
For example, for the thermal kind, because for example, maybe the thermal, the temperature is very, very high. So maybe that in the OS this side, they want to just say, okay, at this time point, you just limited the CPU frequency or limited some device the frequency. So even there have other requirement for the frequency change to other higher frequency, but at the MCU side, you cannot do this because this has been constrained, right? So this just think there are about one case that maybe. Yeah.
So at least as far as thermal is concerned, right? If you look at reference implementations, all the thermal sensors that we have, we do assume that you can map it to your MCU so that the MCU has access to at least all the sensors and can read off them. Yeah. So if the MCU says that I know that the CPU is at 70 degrees and then it receives a request for 3 gigahertz, it automatically knows that it's going to deny it. So in that case, the existing algorithms already cover it. You don't need a specific QoS for that. The QoS that we were thinking over here was mostly like you have a GPU, and the GPU has got 3 frequency levels, or a DDR which has got 3 frequency levels, and you can say that on this GPU, I want a particular tessellation rate, or for a DDR, I want a certain write bandwidth. And then you just specify the bandwidth, and then the firmware moves it into a particular frequency or an idle state. And if you lower the bandwidth, then it can save power on the DDR, it can do self-refresh, and so on and so forth. But we are still struggling to find those kinds of use cases.
Understand, yeah, thanks.
So if you have any other use cases that you think would fit into the criteria, please do let us know. If you are able to intercept within the next specification time frame, we'll be more than happy. And that's why QoS and autonomous power management is something that we have had on our roadmaps, but we have not introduced it because we simply do not have sufficient input to realize what it is. Okay, so this shows the story of SPCI. I just introduced this slide because this is something that's going to happen eventually. So SPCI, as you would notice from these slides, is a transport to SCMI. So SCMI can have multiple transports. So SPCI is one of it. So if you look at the picture on the left-hand side, that's typically how an SPCI compliant system is going to look. You will have multiple entities in your secure world, and your non-secure world can then choose to talk to any of them using the SPCI protocol. If you move to the right-hand side, what that essentially implies is that one of those entities can be an SCMI server or maybe a power control logic, and you could use SPCI to talk to it, as compared to today using a hardware mailbox. So what you will notice is that typically this unit over there, the SPCI box, the small box, and this can be a hardware mailbox, or this can be an SPCI driver, and you will just use the same functionality. So we are trying to build this in. The prototype is getting worked on, so it'll land up sometime, but it's not very soon. It requires its own time. So it's there in the roadmap. And I think that's one of my last slides. Status and next steps, yes. For device management, as I showed, we have a migration path and a long-term kernel framework that we are trying to analyze. There have been some discussions at the Plumbers conference. This time, it seems that we do have some feedback, and a proof of concept is tentatively targeted on the Arm Juno board because everything runs there. Power management is enabled over there. For SCMIv2.0, and this is still in the concept phase, we are still looking actively for new feedback, for new inputs. We are looking at the device management protocol. We are looking at autonomous power and performance management and QoS support. But autonomous power and performance management and QoS support, in the absence of input, we will probably not intercept it. And if we have sufficient inputs and if people are really interested, then we put them in the roadmap or in that specification. So if you have any specific requirements around autonomous power management, QoS support, or anything else, please get in touch with us or anybody from the ARM team, and we'd be happy to help you guys out. So that's all I had. Are there any questions? And okay, last thing, what we did was, very recently we introduced an SCMI blog and an SCMI Power and Performance Management white paper. You'll find all of them on the ARM website. So I'll just go. This is slow. Okay, so what we'll do is, so if you go to the blog, the link is there. It'll at least tell you what we are planning for SCMI and why you should be using SCMI and moving your tasks right now from your non-secure side to a secure side on a microcontroller. Get your power management story fixed out. Get power management working on a vanilla Linux kernel rather than having to modify your kernel each time. And why is it so important to have a single unified kernel that works for power management across all devices? Please go through it. You'll understand the security vulnerabilities, the other flaws, the hardware concerns, and everything else that are there. Look up our white paper where we go into more details as to what this will help for you, specifically if you've got multi-OS transitions where you are trying to support Windows as well as Linux, and then how SCMI does help you by having a unified firmware and moving everything out from the kernel. So have a look, do let us know your feedback, and that's all I have for the day. Thank you, everybody. Any questions? Otherwise.
So how to allow the SCMI side and the Linux kernel side, they have the same page for the clock or the reset or the power domain. This, for example, CPU PSI, I think this CPU state is very easy to align between these two sides. But there have many the clock, for example, for the GPIO or for the USB or the peripherals. So how, for example, in the kernel side, it sent to one command with the string said that the USB I want to power off, but I want to use the USB, the clock. How the MCU side can you have the same knowledge that it needs to control which the clock. Yeah.
Okay, so today the SCMI clock protocol, if you look at it in the kernel, is already interfaced with the clock subsystem. So if you have a kernel driver that is DT compliant with the kernel clock framework, common clock framework, then it already works with SCMI. So it's already there.
Can I understand that the MCU side, it also to use the DT binding to?
No. Yeah. Okay. So the MCU side doesn't use the DT binding today. If you look at the code that we have on the SCP firmware side, you'll notice that the firmware uses. I don't know if you attended this session yesterday, but for clocks, we have a configuration for the clock module. So in that particular configuration, you can list out all the clocks that you have for the firmware, and the firmware can read off that clock configuration, and the configuration file can be separate on a per product basis. So you might have a common clock module in the firmware and different configuration files for each platform, and then as and when you compile for a platform, your configuration gets fed into your module.
Sorry, this is very basic, but why did we deviate from ACPI? Why did we not use ACPI for ARM systems?
Why did we not use ACPI for
Why
ARM
do we
systems?
come up with SCMI? We do have ACPI for ARM servers, but...
Okay, the important part of why we don't want to use ACPI is that most of the ARM devices are DT based, right? And there is actually no indication that people are so willing to move to ACPI because people are used to working with DT. They're happy to work with DT. And if you want to move to ACPI, then that's a new construct. You want to be happy with it. And SCMI works for both. So even if you have ACPI enabled, the SCMI channel is actually an ACPI PCC channel 3. So if you have a controller, an SCMI controller, so the SCMI controller bit is the new power definition mechanism. So if you have a DT, irrespective of a DT or an ACPI, you still will have an SCP, and you still have a channel. So it just depends upon what the kernel community is comfortable with. If the ARM Linux kernel foundation community today thinks that it's okay to move to ACPI, fair enough. If it thinks it wants to stick to TT, fair enough. But that's a call that we cannot take by our own. That's something that the kernel needs to cooperatively decide.
Okay.
Okay, everybody. Thank you so much.